As we've seen, the epic drama of Fermat's last theorem opened with a spark of insight of Fermat inspired by the words of Dauphintus. Those inspirational words arose from a description of one of the most important and well-known Dauphintine equations in human history, the equation connected with the famous theorem of Pythagoras involving the lengths of the sides of right triangles. In this lecture, we'll open by celebrating the Pythagorean theorem and its wonderful history and significance. We'll also discover for ourselves an elegant geometric proof of this ancient result that involves no algebra whatsoever. Formula phobes, take note. Natural number solutions, x, y, z, to the equation x squared plus y squared equals z squared are known today as Pythagorean triples. And here we'll embark upon a search for these Pythagorean triples. Surprisingly, along the way, we'll see yet another appearance of the famous Fibonacci numbers. We just can't escape them. Finally, we'll close this lecture with an important connection between Pythagorean triples and particular points on a circle called rational points. This important relationship between numbers and geometry foreshadows our lectures on algebraic geometry, a magnificent modern area of study that not only provides a deeper understanding into the theory of numbers, but also, at long last, leads to a complete solution of Fermat's last theorem. Well, let's open our story with the ever-popular and much-beloved result of Pythagoras involving right triangles. The Pythagorean theorem asserts that given the lengths of the sides of any right triangle, two of those sides would be considered the legs, and the side opposite the 90-degree angle is called the hypotenuse, then the sum of the squares of the two legs equals the square of the hypotenuse. Put informally, this result can be phrased as the square on the hypotenuse equals the sum of the squares on the other two sides. And what this means is that if we look at the right triangle and actually physically put a square whose side length is the hypotenuse, and then another square whose side length is one leg, another square side length the other leg, then the sum of the areas of those two squares of the associated with the legs equals, in fact, the area of the square associated with the hypotenuse. So this particular version also offers us a visual way by which we can interpret the result in terms of areas of squares. Now, this theorem also provides us with an excellent excuse to enjoy a famous line from Gilbert and Sullivan's Pirates of Penzance. I am very well acquainted too with matters mathematical. I understand equations, both the simple and quadratical. About binomial theorem I am teeming with a lot of news, with many cheerful facts about the square of the hypotenuse. Okay, I know you're saying don't quit your day job, but still, we really will have many cheerful facts about the square of the hypotenuse, which really is reference, of course, to the Pythagorean theorem. Okay, well, back to the Pythagorean theorem in earnest. The result itself was perhaps first recorded in China around 500 BCE. But there's evidence that this theorem was at least implicitly, if not explicitly, used in Egypt around 2500 BCE and Mesopotamia around 1750 BCE. Many years later, around 500 BCE, the Pythagorean Brotherhood independently rediscovered the result, and since that time it bears Pythagoras' name. One of the most famous right triangles is the so-called 3-4-5 right triangle, and we can actually use it to illustrate a special case of the Pythagorean theorem. So that means that one leg length is 3, the other leg length is 4, and the hypotenuse should be 5. And we can check that 3 squared is 9, 4 squared is 16. When we add those two, we get 25, which happily is 5 squared. Of course, As we know, one example does not a proof of the general theorem make. In fact, there are literally hundreds of different proofs of the Pythagorean theorem. Most are either algebraic or geometric in nature. However, there are many others, including some that involve the advanced machinery of calculus. Even a future president of the United States discovered a new proof of this ancient theorem. While serving as a member of the House of Representatives in 1876, James Garfield came upon his novel proof. 5 years later, in 1881, he became the 20th President of the United States. Perhaps more importantly, he was an 1856 graduate of Williams College, although I must confess I never had him in class. Tragically, however, 6 months after being inaugurated, he was assassinated, and thus cut short his political and mathematical career. Well, here we'll now discover for ourselves a wonderful 12th century geometric proof of the Pythagorean theorem attributed to the great Indian mathematician Bhaskara. It truly exemplifies the elegance and aesthetics within mathematical arguments. For one thing, will require no algebraic manipulations at all. In fact, we can really view this more as a puzzle or riddle rather than a proof. So let's take a look at it now. To prove the theorem, we first have to consider, of course, a right triangle. And so here is a right triangle. And I want to prove that this length squared plus this length squared will equal this length squared. So this puzzle involves, first of all, 4 copies of this particular right triangle. So here I have 4 copies. And you can see they're all identical to the original. So they're identical copies of the 4 triangle. And now, what I want to do is I want to arrange these puzzle pieces to form a square where each side of the square is the length of the hypotenuse. So that means that all these hypotenusi should be on the outside. So I'm going to now rearrange this, and this is looking pretty good now, actually, doing this live. Looks like we have a square. Of course, unfortunately, there's an empty hole, but happily I actually have a piece that will fit right in there. So I'm going to add a little extra square. And now you'll notice that I have a perfect square. You might say, gee, is this really a square? Certainly all the sides have the same length because they're all equal the hypotenuse of the same triangle. But what about the angles? Are the angles 90 degrees? Well, it turns out we can show they are. Remember that the sum of the angles of a triangle equal 180. And if this is a 90-degree angle, then this angle plus that angle must add up to 90 as well. 90 plus 90 would give us the 180. Well, that means that this angle plus that angle equals 90, and if I put this back in place, notice that this angle and this is the opposite angle, those two would add up to 90, and similarly across the way. So this angle plus that angle would equal 90. This is an actual square. So the area of these 5 puzzle pieces must be the hypotenuse squared, because it's base times height, which is hypotenuse times hypotenuse, or hypotenuse squared. Okay, well, now what do? Now the challenge is to just rearrange these pieces and see if we can produce one leg squared plus the other leg squared in terms of area. So we can't remove pieces, we can't add more pieces, but if we just rearrange them, the area itself won't change. So here's the great trick to this puzzle. How are we going to take these pieces and form 2 squares, one square that has length the short side and one square which has length this longer side? Well, I'm going to tell you the answers to the riddle, which you can maybe share with your family and friends. I'm going to twist this around to here, and I'm going to lift the whole puzzle up and just twist this one around to here and let everything fall down. And notice that I haven't changed the pieces, no sleight of hand here. All the pieces are still here, but notice that now I have 2 shapes. On the one hand, I have this shape, which looks like a square, and on the other hand, I have this shape, which also looks like a square. Now let's confirm that in fact both of these are square. First of all the angles are 90 degrees by the same argument we had before. But now this side is certainly equal to the longer leg, but is this side the longer leg? The answer is yes, and we know that Because when we think about where this piece came from, it came from this leg. So you can see that this leg is exactly that length. So when I rotate it back around, I see that I have a perfect square, and the area of that perfect square is the longer leg squared. So this part right here is this longer leg squared. Now, what about this part here? Well, by the same reasoning, this little piece here is also a square. This side is the shorter leg, and this side is also the shorter leg, which we can confirm by just putting this right in here. So we see that this, in fact, is a little square here. So the area of this will be the little leg squared. So when I put this back and this back all together, notice I have two squares that just touch each other. The area of this square is the larger leg squared. The area of this square is the smaller leg squared. So what we see is that one leg squared plus the other leg squared equals the exact area of the hypotenuse squared. And there's our proof of the Pythagorean theorem for ourselves. Well, in fact, the converse of the Pythagorean theorem is also a theorem. In other words, if we have a triangle in which the sum of the squares of the lengths of two sides of the triangle equals the square of the length of the third side, then that triangle must be a right triangle. Now, this theorem has a number of practical applications. For example, when carpenters wish to ensure their structure has a right angle, such as a deck, we'd want to have a right angle, they'd mark 3 feet off in one direction, 4 feet off in the other direction, and then measure the distance between those two markings. If that distance is exactly 5 feet, then they know that the angle formed is indeed 90 degrees, and that's the converse of the theorem. Well, with the Pythagorean theorem firm in our hearts and minds, we now move to its connection with number theory. People throughout human history have been fascinated with right triangles whose lengths are all natural numbers. For example, such right triangles were incorporated in several megalithic monuments found in Egypt and the British Isles from as early as 2500 BCE. One famous example of such a right triangle is the famous 3, 4, 5 right triangle that we saw earlier. Another example that we also saw was the 5, 12, 13 right triangle. Well, suppose we have a right triangle in which each side length is equal to a natural number. Then the triple of natural number lengths is called a Pythagorean triple. So the triple 3, 4, 5 is a Pythagorean triple, as is the triple 5, 12, 13. Those are both examples because they conform to the lengths of sides of right triangles where all the sides are natural number lengths. The famous Mesopotamian stone tablet, now known as Plimpton 322, from around 1750 BCE, contains a long list of Pythagorean triples. So, for over 3,700 years, people have known that there are long lists of Pythagorean triples. But are there infinitely many? The answer is yes. And in fact, we're about to prove that there are infinitely many Pythagorean triples by giving an algorithm, in other words, a procedure for generating an endless list of them. Let's just recall that the triple XYZ is a Pythagorean triple if x, y, and z are all natural numbers that satisfy the equation x squared plus y squared equals z squared. In order to describe a process of producing an endless list of different Pythagorean triples, we first consider such a triple XYZ and now claim that x, y, and z cannot all be odd numbers. And I want us to verify that for ourselves. So why is that the case? Well, let's now do this by contradiction to try to get to a logical fallacy. Suppose that, contrary to what we want, we found natural numbers x, y, and z that satisfy the Pythagorean theorem, x squared plus y squared equals z squared. But in fact, they were all odd numbers. Well, so if they were all odd numbers, that would mean that x squared is an odd number, y squared is an odd number, and z squared is another odd number. So we have an odd number x squared plus an odd number y squared. And we saw very early in the course that an odd number plus an odd number, in fact, yields an even number, such as, 7 plus 3 equals 10. So that means that the odd x squared plus the odd y squared is going to yield an even number, z squared. But we assumed that z squared also is odd, and that leads us to a logical fallacy. Therefore, our assumption that we could find x, y, z all odd is false. In other words, there has to be at least one number that's even in this Pythagorean triple. Thus, let's just assume that y is an even number, and let's actually write it as y equals 2 times a times b for some natural numbers a and b. And as we'll see, because there are infinitely many different choices of the parameters a and b, we'll actually be building infinitely many Pythagorean triples. So that's where the infinitude of them are going to come from, the variation in the a and the b. Returning to the Pythagorean equation, if we now solve for the y squared term in our equation, we would just subtract the x squared from both sides, and we'd see y squared equals z squared minus x squared. And as we've seen several times throughout our course, we can factor now the right-hand side of this equation, as we did in the previous lecture. And in this case, we'd see that y squared equals z plus x times z minus x. Also, since we've already written y as 2 times a times b, we can see that y squared is 2 times a times b all squared, which we can write as 2 times a squared times 2 times b squared. And that's supposed to equal z plus x times z minus x. So we have two factors on the right equaling two factors on the left. Well, we now want to solve for the two other numbers in the Pythagorean triple, x and z. One way to do this is to just set one of these factors on the right with one of the factors on the left, and then the other factor on the right with the other factor on the left. So in other words, let's just set z plus x to equal 2a squared and z minus x to equal 2b squared. And that way, this product on this side will equal the product on that side. Well, if we now take these two equations, which we have simultaneously, and we add them together, we see that the x's drop out, and I'm just left with 2z equals 2a squared plus 2b squared, which, after dividing both sides by 2, simplifies to z equals a squared plus b squared. Now, notice that z is a natural number because a and b weren't any natural numbers. So we just found what z equals in terms of a and b. If we go back to the two equations, and now instead of adding them, we subtract them, then in this case, the z's will cancel out, and we'll see that 2x equals 2a squared minus 2b squared, which, when we divide both sides by 2, yields x equals a squared minus b squared. And if we assume that the natural number a is larger than the natural number b, then we see that x is also a natural number. Because I have a big natural number minus a smaller natural number, the difference will be a natural number. So we've just found the numbers in the Pythagorean triple x, y, and z in terms of these parameters a and b. In other words, if we select any natural numbers a and b, with the number a being larger than b, and we let y equal 2 times a times b, and x equal a squared minus b squared, and z equal a squared plus b squared, then, first of all, they're all natural numbers. X, y, and z are all natural numbers. And in fact, x, y, and z is a Pythagorean triple. That's what we just discovered. For example, if we let a equal 2 and b equal 1, then we just rediscover the 3, 4, 5 right triangle. If we let a equal 5 and b equal 2, then we find that x equals the number 5 squared minus 2 squared, which is 25 minus 4, or 21. Y would equal 2 times 5 times 2, which would be 20, and z would be the sum of the squares of these numbers, 5 squared plus 2 squared, which is 25 plus 4, or 29. So we see 21, 20, 29 when we plug into the formula a equals 5, b equals 2. Well, notice that 21 squared plus 20 squared equals 441 plus 400, which equals 841, which indeed equals 29 squared. In other words, we discover the Pythagorean triple 21, 20, 29. Well, because we have infinitely many different choices for the natural numbers a and b, we see that there are infinitely many genuinely different Pythagorean triples. And that completes our proof that there are infinitely many. Well, I can't resist taking a moment to offer another beautiful way of producing infinitely many different Pythagorean triples. This method involves our familiar friends, the ever-present Fibonacci numbers. Really neat. To begin with, we select any 4 consecutive Fibonacci numbers. Now remember, the Fibonacci numbers begin 1, 1, 2, 3, 5, 8, 13, 21. And the rule is we take the 2 previous numbers and add them together to get the next one on our Fibonacci list. So to begin with, we select any 4 consecutive Fibonacci numbers, any 4 Fibonacci numbers in a row. So for illustrative purposes, let's consider 1, 2, 3, 5. Those are 4 consecutive Fibonacci numbers. Now, we let x equal the product of the outer 2 numbers. In this case, x will be the 1 multiplied by the 5, which equals 5. We let the y equal 2 times the product of the inner numbers, which in this case would be 2 times 2 times 3, or 2 times 6, or 12. And finally, we let z equal the sum of the squares of the 2 inner numbers. In this case, z would equal 2 squared plus 3 squared, which is 4 plus 9, or 13. Well, and notice, by the way, those 3 numbers, in fact, give us the 5, 12, 13 Pythagorean triple that we already knew. So we established that triple using 4 consecutive Fibonacci numbers. Now, while we won't work through all the details here, the triple of natural numbers we generate using this procedure will always produce Pythagorean triples. In our specific example, we just rediscovered the Pythagorean triple, 5, 12, 13. In fact, we could have actually started with any 4 consecutive Lucca numbers, if you remember those. Those are the numbers that start 2, 1, 3, and so forth. And we just follow the exact same procedure to generate 3 natural numbers. Those 3 natural numbers that we come up with will in fact again be a Pythagorean triple. Thus we see that certain recurrence sequences will generate infinitely many Pythagorean triples. Once again, we uncover, and we actually have uncovered hidden structure, this time within worlds of recurrence sequences, which we studied earlier, and Pythagorean triples. And this reveals amazing connections that bring together seemingly disparate numerical notions. Really beautiful. Well, I want to close this lecture by foreshadowing what lies just around the corner in our journey through the number jungle. Let's now recall a possibly lost fact from our algebra and geometry days of yore. The formula x squared plus y squared equals 1 describes the graph of a circle of radius 1 centered at the origin 0, 0 in the coordinate plane. And since this is centered at 0, 0 and has radius 1, 1 unit, we call this the unit circle. And by the way, let me just note that I'm going to use, just for the moment, a capital letter X and a capital letter Y to distinguish from the lowercase x, y, z, which make up a Pythagorean triple. Well, let's take a moment to see why this formula really describes the circle having radius 1 centered at 0, 0. Suppose that the point x comma y is a point on this circle. What that means is, if we move over, say, x units to the right and y units up, that point we land on will be part of the circle. Well, notice that if we're starting here and go x over and y up, that if we highlight the horizontal and the vertical move, then we form a little right triangle having legs x, y, and the hypotenuse is the radius of the circle. And that radius, of course, is given to be 1. Therefore, by the Pythagorean theorem, we know that x squared plus y squared equals 1 squared, or 1. And thus, we've just derived for ourselves the formula for the circle. Let's now consider a Pythagorean triple x, y, z, and return to its famous defining equation, x squared plus y squared equals z squared. If we now divide both sides of the Pythagorean equation by z squared, we actually obtain x over z all squared plus y over z all squared equals 1. So we see that if x, y, z is a Pythagorean triple, then the pair x over z comma y over z is a point on the graph of the circle of radius 1 centered at the origin. Now, notice that since x, y, and z are all natural numbers, x over z and y over z are both rational numbers. They're fractions. Therefore, we see that a Pythagorean triple leads to what is called a rational point on the unit circle. For example, if we return to the Pythagorean triple 3, 4, 5, then we see that 3/5 comma 4/5 is a rational solution to x squared plus y squared equals 1. Notice that 3/5 squared plus 4/5 squared is 9/25 plus 16/25, which equals 25/25, and indeed yields 1. This observation implies that the point 3/5 comma 4/5 is a rational point on the unit circle. Both coordinates are rational, and the point lives on the unit circle. Thus, we're closing this lecture with yet another intriguing and surprising connection of ideas. Each Pythagorean triple can be associated with a rational point on the unit circle. In the next lecture, we'll see that this connection works in the other direction as well. Namely, each rational point on the unit circle can be associated with a Pythagorean triple. Hence, we'll be able to connect the question of finding integer solutions to certain Diophantine equations to the question of finding rational points on certain curves. This discovery will lead us to our next adventure on our journey through number.